faces, nice faces. I just don't want to get any trouble from any copyright things. We're going to share that again. Okay, so I'm going to erase this part here. I can recalculate that
Mr.
later.
Dixon,
Oh, yes, yeah.
are there times where we can't use the assumption rule?
On the test I'm going to give you, I'm going to design the question that the assumption will always work for you. So you'll never have to check the assumption in terms of like working out the percent ionization. If you're in university studying this topic, you would actually have to verify that the assumption rule is valid, but you won't have to do that for me. But you do have to still write the assumption statement. So you have to say
Okay.
you still have to say the assumption part. Is that okay?
Yep, thank you.
Yeah, you bet. Okay, so let's go here. Okay, so I always kind of write down what I know first. So I know the solution would have an initial concentration of bicarbonate ion, which would be equal to the concentration of the salt. Um, and so I don't need to times that number by any kind of value because the salt should be in a 1-to-1 ratio with the compounds. There are some questions though where that's not always true, so be careful about that. So if this happened to be like a 1-to-2 ratio, then you'd have to double that number to 0.04. But this case you don't have to do that. So scribble those out. And we know that the hydroxides would be 0 and the H2CO3 would be 0. And what we're saying there is that's the amount of those chemicals that have ionized. So if it hasn't ionized yet from the bicarbonate, that they would be 0 right now. And of course, once the bicarbonate ion ionizes the water, the right-hand side is going to increase in concentration and the left side is going to decrease. So this would go up by a certain amount. So we'll say X, which means it has to be plus X, plus X, plus X, minus X, 0.0200 minus X. And if we stick that into our formula, we get X squared over 0.0200 minus X, all equaling, and I'll just put little ditto marks here because I'm going to use a calculator to work out that number. And then I'm going to write my assumption. So assume that the ionization is very low, that you're pretty much getting the initial number here. I did notice on some people's work that, and I've noticed in previous years, that sometimes this is actually where students make a mistake and they misread the number. And so they enter, 0.2 maybe, or maybe they go 0.002. And so just double check that you use the correct initial amount. So I'm just gonna go back, make sure I did that. So yeah, 0.02, okay? Because if you're out by a factor of 10, that does change the pH quite a bit actually. Okay, so let's say X squared all over 0.0200, and that equals that number over there. So I'm going to isolate for X here. So square root 1.00 times 10 to the minus 14 divided by 4.3 times 10 to the minus 7. And I need to times that by the concentration of 0.0200. Okay. And now I need my big fancy calculator with giant buttons. So 1 times 10 to the minus 14 divided by 4.3 times 10 to the minus 7 times by 0.02, and then I just got to square root that number. So square root that number. And I'm going to ask one of you guys to chirp in here. Did anyone else get a number kind of like that? Fortunately, I can't see you, so. Well, I'm
Yeah,
gonna go. That's good.
exactly like what I got.
Awesome. Okay, perfect. Okay, awesome. Good. Okay. Now, I kind of just write. I know some students asked in class before we went away that this number doesn't have the right number of sig figs in it, and I don't really worry about that right now because that's not my final answer. I'm just kind of writing that down to remember what the number was, and so now I want to figure out what is x referring to, and what am I really being asked to do in the question? Like, what's it really asking me to find? So I'm going to scroll up here just to double check here. So the first thing was it was asking me to find POH, which means I need to know the hydroxide concentration to do that. If it had been pH, I'd need to have to know the hydronium or the POH. And what does the X stand for? Well, the X is the concentration of the hydroxides at equilibrium. So once everything's said and done, that should be how much hydroxide you have in solution. So the concentration of the concentration of the hydroxide would equal this number and the molarity of that number. So I'm being asked to find POH. That's fairly straightforward now. Negative log that number. So I take the negative log of that number. So I keep a number on my calculator. And I go negative log. And I got to take the negative log of that number. And I'm getting like 4.666. Ooh, demonic. 219er, blah, blah, blah. Okay, so now I worry about sig figs. I don't really worry about sig figs at the very end. And because you're using Ka values, generally it's 2 sig figs, although I guess the initial concentration might play out here. But you have a 3 sig fig concentration number and a 2 sig fig Ka number. So I got to round to 2 sig figs. So remember that the number to the left of the decimal, left, they don't count as sig figs. So this would be 4.6, and then it's 6, blah, 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 so 7. Now remember that actually is basic, because if you worked out the pH, then you would do 14 minus that number, and that would give you a pH of 9.33. So that's clearly basic, above 7. And there we go. So I would say that's probably I would think the biggest kind of question you're going to get as far as all the math stuff you have to do. And that might be on the written section. I might have a question on there to make you do that. It's kind of tragic. It's kind of like a Greek play that if you have a compound like this, that's amphiprotic. I mean, we just did a different question, but if you had a compound like this is amphiprotic, or a question involving like this compound, that's also amphiprotic. If you make the wrong call on that, like if you say, oh no, that's an acid, and it might actually be a base, or maybe you say it's a base, it's actually an acid, then everything you do would be wrong after that, like once you make that assumption. So what you have to figure out first is what, well, I kind of erased it here, but you have it in the earlier notes. What we talked about was comparing Ka, comparing it with Kb. And so you would have to decide, for example, these chemicals here, do they have larger Ka values or Kb values? And then that's what tells you whether to set it up as an acid question or a base question. So I hope that makes sense, because you want to be really careful about that on the test, right? Because if you just made the wrong assumption, if for example, when we first did this with NOAA, we showed another reaction that produced hydronium. So if you'd gone with that, obviously you would have got the wrong answer at the end. So that's why I would say this is probably the hardest kind of question you're going to have to deal with on the test. Any other questions you guys want to ask about, or I'm happy doing I have a few more things in my head to review, but I just want to know if you guys had any specific things you wanted me to review. Noah had asked about a question from the previous test, but any other questions?
Regarding the rounding just now.
Yes, yep.
Right. I believe that the digit before the decimal point, doesn't count towards significant digits. Wouldn't it be 3 after the decimal point, or have I forgotten something?
So this just I didn't hear you too well there, but this number right here, I'm going to draw a green arrow towards it.
Yep.
That number there has 2 sig figs.
Yes.
So only that significant. And the reason I use 2 sig figs is the Ka value here.
Oh, right. Yeah, that. Okay. It makes
Okay.
sense now. Got it. Thanks.
But you are right. This is a 3 sig fig number here, like the concentration. But because
Yep.
this is 2 sig figs, we have to go with that one. Okay.
Yeah. Fun meeting. If you go for 3 sig figs, it's 666.
Yes, that's right. Yes, that's right.
Yep.
Yeah, exactly. That's right. Yeah. Yep. I was also asked about send the answers for the quiz yesterday. I believe if I have this right, the POH was 10.77, and the second question, the pH, was 10.63, which I had no idea they're going to work out to be such close numbers, which is kind of cool. I'm just math nerd that way. So anyway, that should be the solutions for yesterday's quiz. Someone asked a question about that. So, okay. The other question was asked, and I don't know if you have access to this, but the test on solubility, there was a multiple choice question, number 9. This would have been the morning test, so multiple choice question number 9. And I actually had to change the answer on it. I think I sent out the marks, and then a student pointed out that I made a mistake with my answer key. And so it was 2 liters of 0.32 molar potassium phosphate. And the question was asking, what is the concentration of the potassium ions and the concentration of the phosphate ions? And so for a question like this, where we're being asked about concentration, I made a mistake about this 2 business here. And just before we answer the question, imagine you had a glass that size, and you had a glass like this size, and it was full of like your favorite, I don't know, drink. And let's say it's pop or something like that. And someone said, well, I want you to drink beaker 1, take a sip from beaker 1 or glass 1, and take a sip from number 2. And this is your favorite drink. This is your favorite drink in both glasses here. And someone says to you, which one tastes sweeter to you? Well, they should really both taste the same, because they're both the same drink. So it wouldn't matter whether you drink it from a big glass or a small glass. And so sweetness is a measurement of concentration. But if these were both packed full of sugar, and someone said to you a different question, like which one's going to make you fatter if you drink it? Well, obviously, if you drink more sugar, you're going to get fatter. So beaker 2 has more sugar. So that would be worse for your health here. So the question that was asking about concentration. So this 2 liters, it doesn't matter whether you had 10 liters or 50 liters or 2 gallons or a quart, whatever it is. The concentration is still constant. It doesn't change between the glasses here. So the potassium ions would come from the dissociation of the salt. So you get 3 potassiums for every 1 phosphate. So the concentration of the phosphate should be 0.32 molar. And then the potassium ions would be 3 times that number, which would be 0.96 molar. I believe when I made my answer key up, I had divided the concentration by 2, and then it had worked out that from there. But in this question, the concentration doesn't matter. If they had asked the moles, though, if they said how many moles do you have, then you would have to divide by the 2 then. Or sorry, times by the 2 actually, in that case. So, okay, so I'm going to move on then with something else that we could look at. But is there any other questions about acid-base stuff you guys want me to go specifically? You want me to go over? Because I have some review stuff I was going to do with you guys.
I have a question for the hydrolysis lesson. The
Yep.
ending cut out, like I couldn't hear the audio. It
Oh,
was
okay.
like the ions. You wrote like alkali ions and alkaline earth metals are spectator ions, and transition metals are acids.
Yes, yeah. So I'll go over an example. If you have your acid-base table in front of you, I can actually, I can show you too on here. So I'm just going to erase this part here, and good. So, but if you have your own table, you could write on your table here to show you this, because this might be helpful on the test. You can bring your own data table in. But if we look at certain ions on here, like this one, and where are we here? This one and this one. And in the margin here, I'm gonna write a compound like Fe chloride. So iron 3 chloride. So this compound here would dissociate. Actually, I'm going to choose. I just got to check something here. I'm not sure whether that might not be the best choice. I just want to check the solubility of this compound. Iron. Yeah, it should be okay. So if you had iron 3 chloride and you put it into water, you would get Fe3 plus and 3 chloride ions. And so chloride ions, although they have a negative charge, they are even under the base column, like they're right there under chlorides. They cannot act as bases. They cannot take protons. And the reason they can't do that is that HCl would be a strong acid, so it would immediately ionize back into chloride. So we know that the chloride are spectator ions. So that's just a spectator ion. Now the iron ion, though, it would be strange if it was a base, because if it was a base, it would have to be able to take a proton. And of course, if you did that, you'd get like Hv4 plus, because you'd have like an H plus and an iron and a 3 plus coming together, and that just does not happen. And so I could see why, like, a lot of students would think, well, this must also be a spectator ion, because how could iron 3 plus act as an acid? And the reason it can is that this compound here is actually iron 3 plus. That is the iron 3 ion. So it's an iron. It's kind of hard to draw this, but it was an iron ion surrounded by 6 water molecules. It makes this really strange complex. So they kind of use brackets around it. And because you have these waters now, you can actually remove one of the waters. So you'll see right here, I've drawn a lot of arrows here, but if you can see here, there's 6 water molecules around that. And when you take one of the protons away, you're left with 5 water molecules and an OH group. So if you remove one of those, erasing the wrong thing here. If I remove one of those and give off an H here, and then I have water, then these things come together to form hydronium, and then you get this compound over here. So if we just look at those compounds, I'm not going to do all of them, but iron 3, chromium 3, aluminum ions, and if you go to your periodic table, how can I show you that now? Let me see here. I'm going to have to go to this. Yeah, that should work. Okay, so share that. And so how do I do that? Go home. Chemistry. Oops. Come on. Sorry, give me 1 second. I'm having a hard time getting my computer working here. So let me see if I can get my mouse working. So I'm not sure if you guys can see that. I think it says, can you see that, Serena?
Yeah.
Good. So unfortunately, I can't draw on this image right now. But if you look at the alkali ions, that's the first column, and the alkaline earth metals beside them, they never act as acids and bases. But all the metals in between, transition metals, they have slightly acidic properties. So those compounds, what I was trying to say in the video is that the first column, I'll use my mouse here, that column there and that column there, they're always neutral in water. But any of these compounds in this area, they have slightly acidic properties because they form these strange complexes in water, these hexaquarium ions, and they tend to have acidic properties. So if you look at zinc, for example, zinc right there, that actually is slightly acidic if you put it in, sorry, the ion zinc is slightly acidic if you put it into water. And things like nickel, they're slightly acidic in water. So the only ones that aren't, that are spectator, would be the first and second column. Is that okay?
Thank you.
You're welcome. Of course, yeah, no worries. So I'll just share my OneNote again. And let's go back to, oopsie. Okay, so let's try just one more question. It's kind of I would think a challenging question too, kind of like the one Noah had asked, but I think it's maybe a little bit less work. And let's say you were told you have 0.010 molar okay, and it has a pOH equal to let me think 11.725. So that's the pOH, 11.725. And the question is, what is the Ka for Ha? So Ha is some kind of acid that we don't know its chemical formula, but we do know its initial concentration, and we do know the pOH of that compound in solution. And we're being asked to find the Ka value for it. So what is the Ka value? So I'll just work through it with you guys, because I know time is kind of tight here, but just to show you the general kind of question. So generally, the fact that it's an acid, and so the reason we know it's an acid is that the pOH is in the acidic range. What we might want to find out is this acid strong or is it weak? Because if it's a strong acid, it really wouldn't have a Ka value, which means it'd be kind of a weird question for me to ask. So it's probably, I'm kind of sort of implying it's weak, but how could we prove that? Well, first of all, if it was strong, we could just find the pH by taking the negative log of the concentration of the acid. So we could try that, and that would give us a pH of 2.00. And of course, the pOH then would be 14 pOH, would be 14 minus the pH measurement. So the pOH should have been 12.00. So it's close, but it's not right there. So this must be a pretty strong acid, but probably close to one of the stronger weak acids. But it can't be it can't be strong, because it should have been 12, and it's 11.75. So what I would probably do is an ice table here. So set up an ice table. Conjugate base, ICE. And I know the Ka expression, that's pretty easy. That would be the concentration of the conjugate base times the amount of hydronium all over the concentration of the original acid, HA. And if I knew those numbers, I could just plug it into the formula then. And now remember, K is just a fancy, or the Ka is just a fancy KEQ. So I kind of need to know this row here. So if I draw my line down here, then I got to work out some numbers here. So I know that this number here is 0.010. That's what we're told in the beginning. It doesn't matter what the water is, it's a liquid. And I know these numbers would be 0 to start off with. And I know that when it ionizes, it has to shift to the right. So we decrease the reactant side, increase the product side. And now I need to get some numbers here. So I need to know what the change is. So that's where this number here becomes important, because that's telling us the pOH, which means I could find the concentration of hydroxide pretty quickly, but I don't want hydroxide, I want hydronium. So I think what we'd have to do is convert to find pH first. Okay, and just before I do that, a lot of times when we start teaching this, these words, I did mention this in a few videos, these words can sometimes make students think we're trying to tell you it's acidic or basic. Like if I said the pOH is this number, students might think, well, he's saying OH, he must be trying to imply that it's basic. But the pH and pOH, they're just numbers. They're just on a scale sort of thing. So it's kind of like talking about someone's height or something. I mean, you might put your own feeling on whether the person is tall or short, but the height's the height. It's just a number. It just tells you what height they are. So same with pH and pOH. It just tells you the amount of chemicals that are there. So if the pOH is 11.75 and I go to 14 minus 11.725, I'm going to get 2. Oopsie. I'm going to get 2.275. And so that would be my pH number here. And this here would give us 10 to the negative 2.275. And so that's how much hydronium you would have at this equilibrium here. And of course, if you go from 0 to that number, then that must be that number. So I'm going to use little ditto marks here just to save me from writing that out all the time. And it's going to have to increase by the same amount because it's 1 to 1. So this would be the same amount here. And then now here you'd be minusing by that amount. That's not the number 11. Sorry, it's like little ditto marks. 0.010 minus whatever that number is there. Okay, so now it worked out quite well for me here that this change here is actually significant. It's going to be quite high actually, because the acid is a fairly strong weak acid. You might remember we said it should have been pH 12 and it's 11.75. So this actually ionizes probably more than 5%. So if you use the assumption rule here, you would most likely get the wrong answer, I would think. So we don't want to use the assumption unless we are solving a quadratic equation. So there's no quadratic here. We just plug the numbers in. So I'm going to plug that in then. So Ka is the concentration of each of those ions, which is the same. So negative 2.275. I've got to square that number. And then I've got to go on the bottom here, 0.010 minus 10 to the negative 2.275. So if you guys could work that out, if you don't mind, just because I'm going to use my calculator here, and it's very easy for me to type in the wrong thing here. So let's see, 10 raised to the negative 2.275. I'm going to square that and divide it by 0.01 minus 10 exponent minus 2.275. Okay, that wasn't good. Okay, so let's do it again. Divided by bracket. And we get a number similar to that.
Yes.
Okay, cool. Okay, thank you. So it has a fairly high K value actually. So I would say that's another fairly hard type of problem. So I would say definitely review review the questions that have been assigned to you, and there will be a couple of written questions where you have to show a fair bit of work, like a question like this or the one above is a fair bit of work. And I would say probably review the stuff on the self-ionization of water. So make sure you're comfortable with that.